Thanks very much. It's great to be here. This is also my first talk since I've entered into the Medicare category. So you can tell me about my precipitous decline in my behavior now that I've crossed over the Medicare line. So I'm going to talk about work that I've conducted over the last about 15 years, but there is not any real new work in this. At the end, I have a brand new experiment that I think is related to the issue. But I'm going to give you a broad overview of my research in movement timing that really began in the late 90s and finished in kind of the early 2012. How do I move this? Okay. So one of the ways we think we control time in motor skills is that we have inside of our brain a little clock. Maybe it's a large clock, but the clock has a representation of time, and it is invoked to control the timing of lots of motor skills. One of the ideas that is very akin to this approach is the notion of what's known as a generalized motor program, because the timing aspects of movements are thought to be separate from the movements themselves. We can apply the clock to a variety of tasks. And so timing is considered to be amodal. But another way to keep time is we can take advantage of some natural regularity in this case in our environment. As the sun does its thing, the dial moves. And so timing in this case is a result of the way our sort of neurobiological systems operate. And we can think of this approach as, we call this timing is emergent. This is not a clock. This is not our original use of the word. This comes back to the work of Michael Turvey and Peter Kugler almost 40 years ago. We originally started studying this question with a very simple experiment. By the way, if I'm too loud with my mic, just kind of raise the hand. I usually don't talk with a microphone. Purdue has a policy that I'm not allowed to have a microphone. Also for content reasons, not just for volume. Okay. So we had subjects do two very simple tasks. One is to tap to a metronome, beep, 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 beep. Metronome goes off, and they continue tapping as though the metronome was on. And they do this at each of 5 periods. 800 milliseconds down to 325 milliseconds per inter-tap interval. Not a hard task. Subjects are pretty good at this right away, and we can measure their timing variability. They also do a second easy timing task. They have about an 8 centimeter diameter circle, and they travel around it, and at 12 o'clock on the circle, there's another little circle. They have to get their finger to cross the little timing circle, coincident with the metronome beep, and then metronome goes off and they keep going. We call this our circle drawing task. The periods are the same, 800 to 325, and subjects are also really pretty good at this. And we can measure the variability in timing. So you generate the timed intervals, and then you can compute the standard deviation, and then you compute it to a percentage of the actual period. So that's called the coefficient of variation. And we asked a really simple question. Dick McGill was one of our subjects, and he turned out to be the best timekeeper in the finger tapping test. He paid me off for that. But then we asked the question, why is he a good timekeeper? Well, one can say he has a great clock. And he's using the clock to do this. His clock is really precise. He's a precise timekeeper. So what about his performance in the circle drawing test? Because he's won the gold medal in tapping at the London Olympics, will he win the gold medal in tapping, in circle drawing timing? Well, we showed that won't happen. And what we have here is a unit circle, and we're plotting the correlations across each of these pairs of tasks. So if the correlation between 500 millisecond tapping and itself is 1.0, so that's where that lies. All of these symbols are the correlations between the two different tasks, between the different versions of the tapping task and the different versions of the circle drawing task. And this small diameter circle, we call it the ring of significance, kind of sounds sort of glitzy, is the value that the correlation has to be significant. And what you see is the tapping tasks correlate with each other. The circle drawing tasks correlate with each other, but tapping and circle drawing are not correlated. So knowing how well Dick McGill does in the tapping task as a timekeeper doesn't tell us how well he would do in the circle drawing task as a timekeeper. This is one of my favorite graphs, and Daniela Corbetta, when she was a colleague with us at Purdue, this was her idea for how to present these correlations, and it really is a wonderful graph. Since she's left, all my graphs kind of stink, but this is really a nice one. Oh, this doesn't work. So that work suggested to us that we don't have a ubiquitous amodal timing system. That there might be specificity in timing, and we took advantage of the fact that Richard Ivory had shown that people with cerebellar damage don't time well in this task. And he was visiting us in 1999, and we sort of made some predictions about what would happen to people with cerebellar damage when they timed in the circle drawing test. And so this is a trajectory of a subject who has lateralized cerebellar damage. So they have a good hand, so to speak, and a bad hand. The damage is in only one of the cerebellar hemispheres. And this is a subject performing in the tapping task. Up top. This is them performing in the circle drawing task where they have to stop for a beat and then continue. And we call that intermittent circles. And then on the bottom is the subjects performing and the continuous circle drawing task. And what we find is that in the tapping task, the cerebellar lesion side hand is impaired. In the circle drawing task, in which they have to stop each beat, which is the intermittent circle drawing, is also impaired, but the continuous circle drawing task is unaffected by having a cerebellar lesion. Let me point out one thing here. These subjects were in their 60s at the time. Those values equal my college sophomores who do the task. So it's not that they are equally bad and there's no impairment. They're performing as a 20-year-old would have performed, and there's no difference. So we took this as nice support for our idea that there are two what we call separable timing systems. One is a clock-like system that we think works in tapping, and then an emergent system that we think works on continuous tasks. And so there's a distinction between discrete and continuous control, and John brought that up earlier, and we've been trying to ride that in a number of our research studies. This comes from an experiment from Becky Spencer, who the previous paper was her dissertation, and this is, I think, one of our favorite experiments. We had people time to the 12 o'clock spot on the circle, which we at the time called the vertical circle. It's kind of a bad name. 12 o'clock is better. Or they had to time to 9 o'clock. But as we have the trajectories, we can make believe they were timing anywhere. So we could ask, when you're timing to 12 o'clock, what's your variability anywhere else on the circle? And the same thing for the 9 o'clock circles. And we do this all the time in our behavior. We came into this room at 8 o'clock in the morning. You might want to awake at a certain time. And let's say you're a little bit early or late in waking up. Somehow you adjust your behavior to be here at 8. And that's what our students do, most of them, for class. They have a lot of variability in other aspects, but the variability kind of decreases at the time they're supposed to be doing something. And in tapping, that's what happens. People are more precise at the touchdown part of tapping than they are at other parts of the trajectory. George NAK had shown that. So we're going to ask whether people are more precise at the timing target than other places. And so this is the result. Let me walk you through this. Here we have the goal duration, 300 to 500 milliseconds. And here we have the detrended variance. Just think of it as the variance in time. And if you want to know the technical part of that, we can sort of parse that out later. Generally, there's a linear relationship between the interval to be timed squared and the variance in time. It's a Weber function. And what we show here is that the Weber function is the same for the 12 o'clock circles when they're being timed at 12 o'clock versus when we're making believe they're being timed at 9 o'clock. And the same thing happens for the circles that are being timed at 9 o'clock when we make believe they're being timed at 12. And in fact, we looked at various parts of the trajectory, and it really doesn't matter where you look. It's as though the subject's using a constant angular velocity strategy to succeed at the task. So here, the strategy that subjects use to time the continuous task is different from the strategy subjects use to time the discrete tapping task. This is some work from Baer et al., in which they do the same Weber analysis of musicians and non-musicians. And what we find here is that musicians turn out to be slightly better timekeepers, and that the drawing movement shows a little bit shallower Weber slope than the tapping movement. So this is, you might think of counterintuitive. Tapping is one joint, kind of really simple. Circle drawing, shoulder and elbow, one might think it's more complicated, but in fact, circle drawing has less variability in timing than the, in quotes, simple tapping task. It's kind of like the difference between riding a unicycle and riding a bicycle. The bicycle looks more complicated, but in fact, those extra degrees of freedom make life easier for you. Where in tapping, if you make a mistake, you pay for it. Where in circle drawing, the joints can compensate for each other, and so therefore you get a benefit from this multi-joint system. This is a detrended fluctuation analysis on the tapping and circle drawing task. This is an individual subject. And the time series, someone tapped for a trial about 580 intervals. It takes quite some time to sit there and do that. And they did that at also the circle drawing. And they did at 580 intervals. It was half a second was the period. And we asked, what is the person's fractal structure? And it turns out that the time series of tapping has 1/f structure, as does circle drawing. And then we asked, how consistent is that? So do you have a signature fractal structure? And it turns out people do. reliability is about 0.8, which is we think is pretty good. But then we asked, is the fractal structure in the tapping time series predictive of the fractal structure in the circle drawing time series? And it's not. And that's the graph down here. So even though we're reliable in producing a fractal structure within a task, that fractal structure is specific to the dynamics producing this compared to this. So we just don't have we don't have an IQ for this fractal structure. We have specificity in producing this. And this was Tori and Balasubramanian, and we kind of did the grunt work on that. This is Bree Studenka's work, and this is the first experiment in her work. This is now, we're using a synchronization task only. Imagine you're tapping beep, 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 and you prolong an interval. And the prolongation or the shortening of the interval is not predicted by the subject. It can occur at interval number n, and it can occur with a big perturbation, a little perturbation, and the perturbation can be long or short. And so this is the interval that was perturbed, and we know in synchronization that tapping makes exquisite corrections to these perturbations in the metronome. And these corrections occur even though the perturbation is not perceived by the subject. So here's in tapping in one interval. There's the error produced by the metronome, and then within one interval, the person's back in line. In circle drawing, people can't make those phase corrections from the metronome. Again, another line of evidence that these two tasks are capturing two fundamentally different timing strategies. And Bree got really clever. She was clever before, but in this study. And we're wondering what's special about tapping. One aspect of it is that it's discrete. I mean, it looks as though it has pauses. But another aspect is that tapping gives you a very salient little bout of feedback when your finger touches the tabletop. Circle drawing, there's nothing distinctive about the tactile feedback going around. So we decided to make it distinctive. We put a very, very thin piece of Velcro at the timing target. So when your finger went over it, you would feel that you were there. And then, as you left the timing target, it goes away. Up on top, you can see there's a board in which we sort out part of the surface. So when you tap, you don't touch anything. So now we've removed that salient feedback from the tapping task. And the idea that we have is that when we introduce the salient feedback in circle drawing, it will start showing evidence for making these phase corrections. And when we remove that salient feedback in tapping, we will lose some of the capabilities to make those phase corrections. And so the tactile feedback is the normal tapping task, which is up here, and what we're calling the rough, in quotes, circle drawing task down here. When there's no tactile feedback, that's when we've cut out part of the board for tapping, and we have the smooth circle drawing task, meaning there's no sort of salient, abrupt tactile feedback. And this is in the eye of the beholder, but you can see that the rapid correction that people make in the tapping task has been attenuated. And In the circle drawing task, the introduction of the tactile feedback improves the phase correction capabilities in circle drawing. And we changed some of the procedures to make the synchronization task work better for us. And that's why in circle drawing, they do seem to show a better job of synchronizing. I can explain that later. Okay. So that's kind of a rough overview of the work that we've used to support what we call the event and emergent timing model. And here I want to ask a question as to people can produce time, what I'm going to call directly or indirectly. In the direct case, it's a goal of the task. That's what a violinist does, I would assume, as I can't play the violin. Okay. That one of your goals is to produce a time structure. But you also produce a time structure now when I'm walking around, although the goal is for me not to have any particular timing for my steps. We're going to take advantage of two robust relations in which people are going to produce the same, what we're going to call movement timing, but under two different situations, and examine whether the timing behavior is purely related to, let's say, the average velocity of the movement compared to whether they're being asked to produce time or not. So I went back to what I knew pretty well and had people perform a Fitts law task. In the Fitts task, you have two targets, a certain distance apart. The width of the target is W, and your job is to go as fast as you can without missing the target. Pretty easy task. Fitts, in 1954, found that the relationship between the target width and distance was logarithmic, and that's known as Fitz's law. About 30 years ago, Dick Schmidt and myself and a bunch of other folks had a different task that produced a different relationship between distance, time, and width, and we'll call that the linear speed accuracy trade-off task, or now that Dick has passed away, maybe we'll start calling that Schmidt's law, in which the subject is given a movement time goal and a target that's infinitely small. They have to move a d unit of distance, and they're told you have to be on time. That is the prime directive. You have to be on time. And your spatial variability and your spatial accuracy, make it as good as you can, but don't give up your timing accuracy. So this is a temporally constrained task, and if you do it repetitively, people will do it to a metronome, like we did the tapping and circle drawing, or we can do it discretely where you give people feedback at the end of each trial. Fitts law subjects don't receive usually any movement time information, and they get to see their accuracy, but we can use our Fitts law tasks and linear speed accuracy trade-off task to have lots of tasks that kind of look the same, where if you would just see a video of the person moving and couldn't hear the metronome, you wouldn't be able to guess whether it's a Fitts law task or a linear speed accuracy trade-off task, unless you could see that they were target widths or not. So the distances are 6, 12, and 25 centimeters. These numbers look strange, but they're doubles, and this is a log to the base 2 relationship. So when you want to look at Fitz's law, they're easy calculations. Once you calculate any one of these IDs, the other ones, you just add 1 or 2 or subtract 1 or 2. So it's kind of an easy way to do the math. And then in the Schmidt task, they had 3 distances and those 4 movement times. And so they do this for about 5 trials. We look at only trials 3, 4, and 5. Trials 1 and 2 are considered as practice. this looks pretty busy, but this is the fits task. These are all the distances. There's the width, distances, and widths. And these are the correlations across the timing variability. So if someone has a certain level of variability in one of these tasks in timing, what does it predict about the others? And what you can see, and this is the yellow highlighted, means the correlation is significant at 0.01. There are 30 subjects. We have a boatload of correlations, and 0.05 just seemed way too liberal, particularly considering the push in psychological sciences to get rid of the p less than 0.05. They're trying to bury it rather quickly. So just use the less than 0.01 as our criterion. So in general, people who have timing variability in one fits law task predict, 5 minutes, I'm in good shape. Timing, no, I'm not in good shape, but I'm good on time. Dick used to always tell me words have meaning. Okay, sorry about that. So within the fits law tasks, timing variability is correlated. Oh, this doesn't work. This is now the correlation between the Schmidt tasks. Okay, I gotta go back. So this is now the timing variability within the timing tasks, the linear speed accuracy trade-off tasks. They're also generally correlated, but they're not as well correlated as I would have expected based upon the timing work that I talked about. Whoops. But across the two tasks, they're not correlated. So your timing variability in the fits law task, if you're highly variable in your timing, it does not predict how high or low your timing variability would be in the Schmidt tasks. Okay, so again, they're unrelated. Okay. Now here, what I'm asking about is the relationship between the actual time produced and their standard deviation in timing. This is not in the Weber form, but it shows us the same thing, that in general, the fits task is more variable than the linear speed accuracy trade-off task. And this makes sense. The fits law task is spatially constrained. Get to the right place as accurately as possible. Be fast. Note there's no timing goal other than make time t small. In the linear speed accuracy trade-off Schmidt task, the goal is to be on time. And so individuals are then matching their behavior to the demands of the task. Oops, sorry for that. Let me walk you through this. Okay. On the x-axis, we have the average velocity that was produced in a particular condition. On the y-axis is a measure of movement smoothness called normalized mean squared jerk. We normalize it the way Toylings told us, I think in 1983 or 87. And so this is capturing the level of the changes in acceleration. I'm not intuitive with this variable, but think about it as when you're sitting in the car and I'm driving the manual transmission. And your head's going back and forth all the time. Okay? Those are rapid changes in acceleration. I'm jerking you around, and that's where the name comes from. Okay? So that's a quote from my wife. Okay? She's actually here, so please don't tell her I threw her under the bus. Okay. So what we have here now is the relationship between average velocity and normalized mean squared jerk. And in fact, if kinematics were just driving this whole thing, then the value of mean squared jerk at 30 centimeters a second should be the same. But that's not what you see here. Well, I'm going to tell you that's not what you see here. What you see is that the fits tasks, except this point I'll explain in a second, at about the same average velocities have more normalized mean squared jerk. Why is that? Their goal is not to be on time. Their goal is spatial. They're making visually based corrections, as the explanations for Fitz's law describe. And in order to change the trajectory that you were previously on, that requires a change in acceleration. And normalized mean squared jerk captures it. What's the best way? What's a much better way to be on time? Produce a sine wave acceleration function. Have a positive acceleration that is equal and opposite to your negative acceleration. And so when you adopt the timing strategy, that then lowers your normalized mean squared jerk. So here are movements with, I'll say, the same average velocity, but their normalized mean squared jerk is also capturing the strategies that they're using in these two different tasks. And so in the future, I've contacted Neville Hogan, who has a very nice algorithm to actually allow you to do a much better job of sort of pulling out these corrective actions. And we're trying to get that to run, so hopefully we'll be able to present that in the future. And sorry for the technical issues, and thanks, and I guess I'll answer questions.